Okay. All right. For geometry, we're doing 7-5 today. And so we skipped 7-4. You're going to get to that tomorrow. But I wanted to make sure I was here for 7-5 because these inscribed and circumscribed circles can be kind of confusing. So they're not terrible, I promise. But so our objectives, we're going to apply formulas for the areas of regular polygons, but some of those formulas come from these circles. And then 2, we're going to verify and apply expressions for the lengths of the apothegm.
The what?
The apothegm. Not Gotham, but close. And the radius of an equilateral triangle. All right, so to get us started, we're just going to review some things that we kind of already know. So circles can be inscribed in, so that's the circle inside, okay, and circumscribed about, so the one outside of your polygon is the circumscribed circle. So inscribed is inside, okay, and the circumscribed is outside, so kind of like if you think of circumference around the outside. It's around the perimeter. Of inscribed is in. Yep, you got it. Okay, so these can be around any regular polygon, and their centers are also the centers of the polygon. So the center of this, both of those circles, is also the center of the polygon. Okay, and that's going to help us identify some terms that we need today as well. So from the center to the vertex is what? It's labeled R. What word would that be?
Radius.
The radius. R is the radius, okay? So that's okay because we had it up here, right? So R is the radius. Then, okay, but notice that radius goes from the center to the vertex, but that's also touches the circumscribed circle, the circle on the outside. Whereas we have A, our apothegm, what does it go to? It goes to the side of the polygon. Perfect. Okay, it goes to the side of the polygon. And it also touches which circle?
The middle.
The middle, the inscribed circle. Okay. Very nice. So R is radius, A is apothegm. What's the C stand for?
Circumference.
Not circumference.
Center.
Center. Okay, because it's the center of the circle. And what's the S stand for?
Side.
The side. So the side length of our polygon. So there's a lot of things in there.
Circumscribed always touch every corner.
Of a regular. Yep, that's a good point. Yes, if the circumscribed will always touch every corner, every vertex, and yes, it will. And the inscribed will always touch every side. All right, so now we're going to review a little bit about this area addition postulate. I can't seem to get this box to go away today. So there it goes. Okay, just takes its time. So according to the area addition postulate, the area of any polygon, which we talked about before, but can be found by dividing the polygon into triangles and then adding the areas of the triangles. So in this case, we have a pentagon down here, okay? And so this is how we do it. We draw segments from the regular polygon center to each vertex. So if I draw from the center to every vertex, okay, it divides the polygon into n isosceles triangles. So n number. How many did I get here?
Is
5. Okay.
Wait a minute. Depending on the size, is that how many triangles there are?
Correct. So if you have 5 sides, you're going to get 5 triangles. If you have 6 sides, you're going to get 6 triangles. If you have 12 sides, you're going to get...
But the lowest you can get is 4 sides, correct?
Correct. Because it's any polygon. Okay.
So a triangle's not a polygon?
Well, it is a polygon, but if it's already a triangle, we can't divide it into a triangle. All right. So this is how we do what?
But they wouldn't be equilateral, so.
Right. All right. So we drew the segments from the center to each vertex We have a 5-sided polygon, so we got 5 triangles. The base of your triangle, we need to identify some of these parts. So the base of the triangle is a side of the polygon. So if we want to look at this one, this is my side, but it's also the base of my triangle. Just like down here would be the base. Okay. The legs are the radii of the circumscribed circle.
What?
Okay, remember if we had a circle on the outside of this, the leg of the triangle, so this one is the radii. The legs of the triangles, because it's isosceles, are the radii to the circumscribed circle. So if we had that circle on the outside. That's the same thing as the radii. Does that help? Okay. And then the altitude to the bases are the radii of the inscribed circle. So the altitude is here. What is another word for the altitude we just talked about? A is altitude.
Oh.
It was like Gotham.
So known as
Apothem, okay, or the apothem. Okay, but that says it's touching if we inscribed the circle, because remember the inscribed circle touches the sides. It would be the radius of the inscribed circle, the apothemus. Which you don't see all that stuff, but I want you to know what they're talking about when they say these. Like,
I'm still trying to figure out why we need circles.
the circles just they're how they have discovered these things, and so giving you the link. We don't actually have to have the circle, but that's how it's describing it, so you can know. It's how they've proved these things. Okay. But yes, we don't have to have the circle as long as you know where the base is, where the radius is, where the side is, and where like the apothegm. And so again, so these definitions down here are revolving around with the circle. So the radius of a regular polygon is the segment that joins the center and the vertex is the radius. So the center to a vertex is a radius of your polygon. The central angle of your regular polygon is the angle formed by 2 radii that are drawn to 2 consecutive vertices. So your central angle is this radius to this radius. That's a central angle. What can you tell me about all the central angles? They're all congruent, yeah, or all equal, absolutely. Okay, and the last one is the apothegm, okay, of a regular polygon. It's that perpendicular segment that joins the center with the base is the apothegm. We might call it the altitude of an isosceles triangle. It's also a perpendicular bisector of the side. So what does that mean? It's perpendicular to the base, which is the side of the polygon, but it's also a bisector.
It also connects to the center.
It connects to the center, but what does bisector mean? Okay, the bisector part means it cuts this in half perfectly. So this half is congruent to this half. So it is perpendicular, but it also cuts that line, that side, in half. Okay, so there's a whole lot of information just starting there for us today. Great answers, though. You guys did awesome. All right, so example 1 is, okay, let me pause this for a second. I can tell you later. It's already started. Okay, so let's look at example 1. We want to find the following angle measures in a regular octagon. So A, the measure of a central angle. Name the central angle for me, first of all.
Central angle. P.
Okay, P would be a central angle. Yes, right? So we're going here. So a better name would be like angle QPR. Right? R. So that is a central angle. So how are we going to go about finding the measure of it?
360 divided by how many angles there are.
Okay, why did you say 360 divided by how many angles there are? Okay, so if we start at one place and we go all the way around and we come back, how many degrees is that? 360. Every polygon, all the central angle is 360 degrees. So we're going to take the 360 degrees and divide it by the number of triangles, or the number of angles in this case. So I'm going to write triangles though. So if we've got 360, how many triangles are in this shape?
4.5.
How many triangles are in here though?
8.
Do we agree that there's 8 triangles? All right, 1, 2, 3, 4, 5, 6, 7, 8 triangles. So what's 360 divided by 8?
45.
You agree with that? Okay. So the central angle is 45 degrees.
Almost just put 45%.
Nice. How about the measure of each base angle in the triangles formed by consecutive radii? Okay, so let me erase some stuff here. That was our central angle. So now we need our base angle. What would a base angle be? QR what? QRP?
No, QR.
QR is not a base angle.
Oh, it's a base angle? I thought it meant
Yeah, base angle. So what do we think? QRP? This would be a base angle? Okay, I see some head nods. Yes. All right. So how are we going to find the measure of each base angle? So first, let me ask you a couple questions.
360 divided by 16.
It would not be 360 divided by 16. Okay. So let's think about this. We divided the shape into what this octagon into what shapes?
Triangles.
Triangles. Okay. So so we've got this triangle here. What kind of triangle are these? They are isosceles triangles because these radii, right, from the center to the vertex is equivalent or congruent, which means the two base angles are also equal. We would do 180 minus 45, yes, right, because this whole triangle is 180 degrees. So what's 180 minus 45? It is, yep, it's 135 degrees.
Divide by 2.
We need to divide that by 2. Why are we dividing it by 2? Because both of those angles equal that. All right, so what is 135 divided by 2?
16.
I mean, I would say, would it help if I did it this way? We got 6 and 12 and 15, and I heard a 7, right? So, oh, sorry, there's the 1, so 0.5. Perfect. So your base angle, each base angle is 67.5 degrees. Awesome job. Those are great connections. You feel good about it? Woohoo! Raise your hands up. I did awesome. I didn't do awesome. You all did awesome. I'm saying you should say, I did awesome. Okay. Then we have 2 theorems. Can I keep going, or are you writing this down? Okay. So our 2 theorems then are the radii of a regular n-gon divide the polygon into n-congruent isosceles triangles, which we talked about. And they form congruent central angles with the measures of 360 degrees divided by n. You guys just figured that out. You just walked through it, explained it to yourselves. That's all this theorem is implying, or is telling us, is what you already had deduced in your mind. Okay. Now, two other things with this. This implies that all base angles are congruent, which, Lucas, you told us. And two, it implies that each radius bisects an interior angle. What does that mean? Splits it in half. Nice. Okay, so let me go back for just a second then. So if that's the case, and we just solve for this angle, which is 65 degrees, and the radius bisects this angle, we, one, know this angle is how much? 65 degrees. And because it bisected, we know this angle equals how much?
130.
130. Okay. So, and I know those weren't the right measurements for this one, but I'm saying if that's the case, you know a lot of information from that few pieces that we just figured out. So awesome. Okay. Now then, the other thing that we have, the area of a regular polygon is 1/2 the product of its apothem and its perimeter. That's a weird formula for area. But, okay, if we think our apothem is this part, and the perimeter is the distance around. So if we found the area of a triangle, don't we do the base times the height? 1/2 the base times the height?
Yeah.
Okay, so to find the area of the whole thing, instead of just doing one triangle and multiplying it, we just say, oh, well, it's going to be this triangle, and the base of that triangle, and the base of this triangle. We just use the perimeter instead. It's kind of weird, but it's a handy shortcut. So let's actually try that with this one. We want to find the area of the regular octagon. We want to use this formula. So the A here stands for what? Apothem, which looks like a Q. And what's the P here stand for? Perimeter. And it's the perimeter of the polygon. Okay, so let's put it into place and find the area here. I can't erase my, oh, there we go. So find the area of the regular polygon. So do we have would I turn the 10 into a 5? Good question. Why would you turn it into a 5? Okay, but so if we think about this formula, A equals 1/2 the apothem times the perimeter. A equals 12.1. Awesome. P is only a side length. So our perimeter is going to be 10, 20, 30, 40, 50, 60. So P equals 80 centimeters. Does that make sense? But then you would half it, but we've got to get the perimeter first. Okay, which one would you have? Yeah, I would half the 80 and the 40 first. To get 40. So then we've got 40 times 12.1, which is 484, and its area, so what's my unit? Centimeters squared, right? Area is always squared. So that's it for that formula. But again, if we had found, we could find the area of the one triangle here. So we could do the 1/2 of 12.1 times 10, because the base would be 10. And we would have gotten 5 times, let's see, this would be times 10 would be 121 divided by 1/2. So 50, yikes. So let me go back. So this would be a half times 121. Does that make sense so far? Right, 12.1 times 10 would be 121. So half of that would be 60.5 would be the area of just the one triangle. But if we want the area of the whole polygon, how many triangles are there? 8. So I would have to take the 60.5 and multiply it by 8 to get all of those in there. And so 60.5 times 8 equals, what do you think? 484. So we could do it that way, and this way is not wrong. Find the area of one triangle and multiply by how many triangles there are. Or you can use this abbreviated equation, if you remember it, okay? That 1/2 the apothem times the perimeter. It's kind of crazy how you can just use the perimeter instead of finding the area and multiplying it. Does that make sense why you can use the perimeter, though?
Yeah.
Okay. All right. Next up, we're going to find the area of the hexagon.
Nope.
Okay, so find the area of the regular hexagon. So let's have you guys do this one. Oh, you don't know what the apothem is. So what do you think?
So do you find the 4 inches perimeter?
Yep, we can find the perimeter. Good.
24.
Yeah, the perimeter is 4 times 6, right? Which is 24. And we said we don't know the apothem, so how do we think we're going to go about that? We don't know the area. Technically, yes, you don't have enough information because you would have learned it in 7.4, which I didn't teach first. So let me do, I'll have to kind of reevaluate your homework to see on this one. Well, no, that won't be it. So let's go ahead. How about this? Let's find the measures of the central and the base angles. Let's practice that.
Okay. And we know 4 already?
Yeah.
Okay. So the base angle. Base angle Q, base angle Q, and base angle.
So remember the central angle is going to be here.
Yeah.
All right.
So 360 divided by 6, 60.
Okay, so we're going to do 360 divided by 6, which means our central angle is 60 degrees.
And then our other angles, we don't know yet. We know they're congruent to each other.
Hold on just a second. You know they're congruent.
Do
180
180 minus 60.
minus 60.
And then you get 120 and then 60. So it's an equilateral triangle.
Okay, equals 120. Hold on.
Which means all the sides equal 4 inches also.
The 120 divided by 2 because we know that these two angles are congruent to each other. All right, so that equals 60, which means, like you said, that this angle is, all three angles are equal, which makes that an equilateral triangle.
And then we know that all the sides equal 4 inches.
Okay, because you know, well, actually, you know this is not equilateral.
Equiangular.
You know it is equiangular. It's an equiangular triangle. But because of that, you do know that all the sides equal 4 because you know equilateral and equiangular. Okay, so what you will learn tomorrow in 7.4 is we're going to talk about when we have equilateral or equiangular triangles. You can cut, there's a bisector, a perpendicular bisector that comes in here. And so a bisector, right, bisects the central angle, which means now that that angle is how many degrees?
30.
Okay, so this is 30 degrees. This angle stays the 60 degrees. We didn't do anything to it. What's the perpendicular bisector angle?
90.
Okay, so this one is a 90. So tomorrow you're going to learn some special.
This one doesn't tell us how to find the area.
It doesn't, but tomorrow you're going to find some special properties of 30, 60, 90 triangles and 45, 45, 90 triangles, and like a connection between their side lengths. So, like I said, when I decided to teach these out of order,
The theorem that we just learned too?
does it go with the theorem we just learned?
Yeah, like Thursday we learned that theorem. I forgot what it was called.
Yes, they're kind of
6, 8,
connected.
10, 1,
Oh, the special triangles? You mean 3, 4, 5?
No, there's 6, 8, 10 too.
And well, yeah, they're 6, 8, 10 because it's yeah. Those are special triangles, yes. And so then, but there are special properties. And if we have a 30, 60, 90 triangle and we know one side length, we can actually determine the other side length.
Does this one go now in special class?
Yes, it does. You're in special class. Geometry is a special class. So we can't actually finish 3 because, like I said, I took them out of order because I wanted to be here to explain the inscribed and circumscribed circles and how they relate. So the last piece here.
Oh, I have a question.
Okay.
The two circles, do they have any like equalness to them? Like, is the inside one half of the outside one?
Nope, because it just depends on the shape. There's no relationship between them currently. Okay.
You never know. They could be dating outside of work.
They could be. It's possible. All right, so the other thing with the equilateral triangles, which is, I just showed you, they can be divided into 30, 60, 90 triangles, which can be used to find the lengths of the apothem and the radius. And there's a couple different ways that you can do that. So these are formulas to help you find the measures of the apothem. You would do this one if you knew the height of your triangle. You would do this one for the apothem if you would knew the side length of the triangle. And then to find the radius, you would use this formula. Okay, so that was just kind of an add-on at the end of the chapter. There aren't any examples or anything like that that go with it, but just those formulas are there. All right, then you guys can get started on your homework.